The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, welcome to today's presentation. My name is Michaela Magnuson and I am part of ERG's webinar support team. Before we get started, let's review a few housekeeping items. Audio is available for this presentation through your computer's mic and speakers or by telephone. Your call-in number as well as your access code is in the control panel box on the right-hand side of your screen. All attendees have been muted to minimize background noise. If you have a question during the presentation, please type it into the questions box on the upper right-hand side of your screen. We will have a dedicated time to answer questions at the end of the presentation. If you are experiencing any technical difficulties, please send me a message through the chat and I will troubleshoot the issues. And with that, I will pass it over to our speakers.
Thank you, Michaela. Thanks for being here today. And we'll have a chance in the next hour to talk a bit about pollution prevention opportunities that relate to ammonia refrigeration systems and the emissions of refrigerant from those systems that are commonly used in the food and beverage sector. I'd like to just acknowledge and thank the members of this team. My name is Doug Reindl. I'm a professor in the Department of Mechanical Engineering and director of the Industrial Refrigeration Consortium here at the University of Wisconsin. And the rest of the team, Mark Kloss, John Davis, and Todd Jekyll, our IRC staff. Mark and John are researchers and Dr. Jekyll is a scientist. And we also had Jake Raylis, who is an undergraduate research intern. And I'd like to give a special thanks to Mark Kloss for a lot of the work that he did on this project. We would not have been able to make the progress we did without the heavy lifting of Mark. And he's going to co-present with me today. So Mark, thanks for all of your work on this project. We had a pretty simple goal at the outset of this project, and that was to reduce fugitive emissions from ammonia refrigeration systems. And our nominal assumption in establishing that goal was really pretty simple. We sort of believe that fugitive emissions collectively were a significant component of the refrigerant losses that these systems experience on an ongoing basis. So that was what we might call our null hypothesis. So during the course of the project, we had several sort of steps or phases in the work. The first thing was to establish some consistent guidelines for determining the refrigerant inventory for these systems. A lot of times the losses are expressed as a percentage of the refrigeration system's operating charge or the inventory of refrigerant in these systems. And unlike a smaller refrigeration system that has a easily metered amount of refrigerant that goes in to allow the system to operate, it's not so easy when you get into these large refrigeration systems. And I'll sort of illustrate that as we get into the presentation. We then moved to the laboratory phase of the effort. We wanted to evaluate different sorts of technologies that potentially could be used to identify where refrigerant emissions may be occurring from these systems. And then in the laboratory, quantify what sort of leak rates we could measure in order to be able to be confident when we went out into the field, which was the next phase of the project. We visited 5 facilities as part of this effort. We baselined the inventory of their refrigeration systems, and then we did a number of plant visits to identify and quantify fugitive emissions of refrigerant for those systems, as well as evaluating purchases for the past 3 to 5 years for each facility in order to try to match up with the field data that we collected on the fugitive emissions with their actual consumption of refrigerant, and then compiling obviously the findings and recommendations that we'll share, most of which with you today. So just to kind of level set fugitive emissions, what we define as fugitive emissions are those unnoticed or undetected refrigerant losses from these systems that can occur either on an intermittent basis or on a continuous basis. So that's a bit on the project and kind of what our goal and intent was. Let's talk a little bit about the background. I know we have a pretty diverse audience here, so I want to give you a little bit of a sense of the background of the technology. what is typical of refrigerant emissions. I found the survey results that a number of you responded to sort of interesting, so I'll show you that data. I'll touch just briefly on how we establish what the operating inventory is for these systems, and then we'll get into what strategies you can apply to reduce emissions and some of the findings from our field work, and we'll finish up with some conclusions and recommendations. So in industrial refrigeration, the food and beverage sector really relies on refrigeration as a part of their business. It's what I call the #1 unlisted ingredient in food products. The end users that manufacture or store these products rely on refrigeration, and they realize that if they don't have refrigeration, they can't manufacture product, they can't package it, they can't store it, they can't distribute it, and all of that leads to no business. So they value the reliability and the safety of this infrastructure, and they actually need it as a lifeline in their business. So in the industrial refrigeration world, the refrigerant that's used by and large is anhydrous ammonia. So there's a number of reasons for that. It's historical, it's been used for a long time. That was one of the first refrigerants that was used in the industry, and they sort of never looked back. These systems are custom engineered, which presents a number of challenges, and it also makes it incredibly interesting. But they're engineered for the specific needs of the facility, the process needs, the temperature needs that they have for their manufacturing operations and storage. So these are all sort of one-off systems. They're not something that are easily sort of packaged and built in a factory and shipped to the job site. These are all field directed, and they're large and fairly complex systems. And they have a lot of different components, and they run 24/7, 365. They virtually never shut down, because everybody needs to eat. So why is ammonia used? We have a lot of different refrigerants that we could use and that are used in air conditioning and other types of refrigeration applications, but ammonia is sort of ubiquitous in the food production and storage sector because it's a really good refrigerant. It is efficient, it has good thermodynamic properties. The cost of the refrigerant itself is low, and it's recognized in the last 10 years or so. It does have some very nice environmental attributes. It has no ozone depletion potential and no global warming potential. Another sort of hidden feature that we used in this project and that some plants use is that it's what we would call self-alarming. What does that mean? That means that you can smell it easily. Most people can detect the presence of ammonia down at pretty low concentrations. It has an odor threshold of about 5 parts per million. Once you get up to about 25 parts per million, that's equivalent to NIOSH's recommended exposure limit. At higher concentrations, 300 parts per million is a concentration that is what we refer to as immediately dangerous to life and health. And then as you get up to significantly higher concentrations at 40,000 parts per million, that is 25% of the lower flammability limit. So pretty low concentration, most people can sense that it's there. So the scale of this infrastructure in terms of how much ammonia circulates through the piping and all of the components in these systems varies really widely. We have small process systems and small applications like ice rinks that might use ammonia systems that contain 500 or less pounds of refrigerant, maybe up to about 1,500 or 2,000 pounds. Small to mid-size or beverage processing, food processors might have systems that now start approaching this benchmark of 10,000 pounds, which is a point of transition from a regulatory perspective that they move into being covered by OSHA's process safety management and EPA's risk management plan programs. And you start getting into medium size food and beverage, they might be 10,000 up to about 60,000 pounds. And that would include some modest size refrigerated warehouses to large size refrigerated warehouses and distribution centers. And then you get into the large and mega refrigerated distribution. Those are in the, let's say, 60, 70,000 pounds in excess of 100, 125,000 pounds. And then you get up into the very large process systems that can go above 500,000 pounds of ammonia in one system. So, there's nothing that's typical. Everything, there's a lot of different sizes of system, scale of this infrastructure. The numbers that are included in these bars, by the way, are reflective of the number of facilities that have refrigeration systems that are included in EPA's Risk Management Plan program. And we know that because they have to file their programs with EPA. The smaller systems that are below 10,000 pounds, there's no compelling filing requirement, so we don't have a very good count. Industry estimates that there's somewhere in the range of 8 to 10,000 of these systems that are below that 10,000 pound threshold. To just give you an idea of sort of the scale in terms of quantity of refrigerant used in these systems. So let me touch just briefly on what, I sent out a poll on Monday asking people to respond to say, hey, what do you think would be a typical loss rate from these systems on an annual basis? What percentage of that system charge do you think is typical of this infrastructure? And I gave you choices: 1%, 5%, 10%, 20%, and 30%. And then I know it's a diverse audience. Some of you may not be at all familiar with this, so I put in, I have no idea. So you can see the results here. There were 148 responses. Thanks for responding. And most of you said a typical loss rate is about 1%. I like optimism. I really do. This is what was interesting. I see what would be a threshold for plants to take action if they exceed that limit. So if I'm losing more than X% of my system charge on an annual basis, are we going to get out and look for where's the ammonia going? What was interesting is you said the typical was 1% and the actionable was 5% of the system charge. So I guess the optimist part of you collectively said that we're doing better than actionable, right? So if we're at 1% typical, no action required. So hold that thought, because we'll come back to that at the end of our presentation. To kind of give you a basis for comparison, Section 608, EPA Section 608, this is part of the Clean Air Act that governs what we call Class 1 and Class 2 refrigerants. These are ozone depleting substances. Any system that has 50 pounds or more of refrigerant and has annual loss rates that exceeds these limits. So industrial systems would be 30% is the limit. EPA said, hey, if you exceed that threshold, you must go find and repair leaks. So think about that, 30%. For commercial systems, it's 20%. These would be what you would find in supermarket refrigeration applications. And then for all others like air conditioning systems, it's 10%. But what's interesting is you keep in mind that these only apply to ozone depleting substances. Ammonia is not an ozone depleting substances, so it's exempt from these requirements. And the only reason why we raise it is because this sets a bar here at 30%. So if we had ammonia systems leaking at 30% as a routine matter, that would be a much different picture, and I think it doesn't match up with your instincts as well. But over the course of many years, we've been at this for a long time, we've seen plants that have leak rates of less than 1% per year, and we've seen plants that have had leak rates at more than 100% per year. And that really was what drove us to pursue this project. And we said, well, why is that range so wide? Where are these losses coming from? Or, I mean, is it fugitive emissions of ammonia that's driving this? What is a reasonable loss threshold, since there is no sort of compulsory requirement from a regulatory perspective, like there was in Section 608 for ozone depleting substances. So the first step in this process is really baselining what is the operating charge or inventory of ammonia in a built-up refrigeration systems for a given system. And so there's kind of three general ways that we can go at this. One is we can do the engineering calculations, knowing all of the components that comprise the system, the state of the refrigerant that's in those components. We can sort of go through and add things up, each component at a time, doing engineering calculations. That's what we did in this project. we could look at, if it's a new plant and they bring in ammonia and they charge the system, we can add up the receipts for a new facility, but a lot of these facilities have been operating for years, in some cases decades, so we don't necessarily have that. And then the third approach is what we call gravimetric, and that is you can pump down the entire contents, in theory, of a refrigeration system, put it into a tanker truck like what's shown here, and actually go off and scale it, weigh it, and then put the ammonia back in. Well, that's pretty disruptive, and for larger systems, it's not really practical. You're not going to pump down a 500,000-pound system. It's going to take you a long time to get enough trucks, and you can't do it. So we're going to do the engineering calculations, and to do that, we evaluate the system, look at all the components in the system, establish what the state of ammonia is in those components, knowing the properties of ammonia, the volume of the volume of those components. We can multiply the liquid volume times the density. Liquid's the most important. It's the most dense fluid. Vapor is going to be fairly minimal in terms of its quantity. And we sum up all of the individual mass of ammonia that is in each part of the system, and we arrive at a total system charge quantity. Some of these plants will have a stated charge on a placard outside of the plant, and what we found is a lot of times the placarded amount maybe doesn't agree too well with, you know, a detailed look at engineering calculations. So this information and what I would say the recommended practices for doing these inventory, these charge calculations, we've sort of memorialized in this guidance document, and this is going to be one of the pieces of information that will be made available at the conclusion of this project. So in addition to talking about the best practices for identifying and reducing fugitive emissions of ammonia, is the details that go into the charge calculations. Given that we only have an hour here today, I apologize, we're not going to be able to, you know, solve any ordinary differential equations or, you know, get into a lot of math. That information is in the guidance document, and we've compiled that and put together some tools that would allow you to actually do these calculations without going through all of the math. So there's a handful of tools that we produced and are available for you. A charge calculator that will let you determine the inventory and pressure vessels, whether it be a horizontal or vertical oriented vessel, heat exchangers like evaporators, and then also compressors. So each of these are standalone tools to calculate the quantity of ammonia in those individual components. And then we also have an integrated tool that is web-based that does the same thing, and it brings also piping in, lets you calculate the quantity of ammonia in piping and basically do those calculations for each of these components, and this will add all of those subsystems together to come up with a total system charge or inventory estimate. So those will be available at the links, and I think what I'll do is at the conclusion of our presentation today, I'll send out this this PDF of this presentation, and you'll have those links. And I know that EPA will have this available on their website as well, the presentation. So that gives you a little bit of background. And so I want to sort of transition now into the strategies that we applied for finding these fugitive emissions in refrigeration systems. And I'm going to turn it over to Mark.
Thanks. So when we first went out into the plants, one of the main goals was to find leaks. And typically how leaks are identified in these systems will be through an odor report. So either utility staff, others, plant staff, or contractors will smell ammonia, they'll put in a report, and then the report will be investigated. And then once it's investigated, they'll pinpoint the source with either a sulfur stick or a litmus paper or some other means, and they'll repair it and go on. Ammonia detectors, either handheld or fixed, typically they're used for either kind of an early warning of a larger release or an emergency response. So a handheld might be used to monitor room concentrations, and at a certain point that'll direct how the emergency response goes. And fixed detectors, they'll be found in machinery rooms, penthouses, other spaces, and they'll alarm at a certain concentration of ammonia. Relief vent line sensors, that is an ammonia detector directly in the vent line. So these relief valves, for their pressure relief valves, they open on high pressure, and they are usually directed outdoors through piping. And so this vent line detector will be near the outlet, and it's typically a high level detector. So it'll start alarming at it'll start detecting at 3%. It might alarm at higher than that. And thermography, which is taking a thermal image of an area and looking for a signature of leaking gas. Quantitative means of looking for ammonia leaks would be bagging, and we'll talk about that next, with an ammonia detector, or ultrasonic, using a ultrasonic detector to pick up the ultrasound generated by fluid flow, and then taking a dB, or a sound power reading from that flow to estimate the rate. And so on to bagging, or screening first. So in screening, what we'll do is we'll take an ammonia detector, preferably with a pump built in. So this particular detector moves about a cubic foot per hour. And the tip of the probe, you get it as close to a potential leak site as possible. Sometimes it's not possible to go directly against it because of grease or accessibility, but as close as you can get, and you move along the leak site and just monitor the screen for a detectable amount of ammonia, and this reads out in ppm. And what we found is even when there's no odor present, you could detect leaks through this means well below the odor threshold. And then it takes a little moving around to find the peak point, but you can find very small leaks. And then to actually quantify the leak in a more accurate way, what we can do is encapsulate the leak site in a bag. So in this picture, it's a fairly large bag. It covers a flange, a valve stem, and everything else. You could also make smaller bags over individual components. It's really up to what you're looking for. But the purpose of the bag is to encapsulate the leak site, and the goal is to move air from outside the bag into the bag. So what we'll do is either the tape on the right side will be loose, or you could put some holes on the right side to direct air through the bag over the leak site, and then either through the ammonia detector sampling pump alone or through an external vacuum pump. And then by knowing the flow rate of the air and the concentration of the ammonia, you can get an accurate calculation of the leak rate. So what we found is the most effective means of finding these releases is what we've been doing for the last 100 years, which is odor reports. Typically, we found that even fairly small leak rates are able to be smelled if you're passing by. And then some areas are not often passed by people, so you could do periodic screening of potential leak points that are high up. You could maybe put an ammonia detector on a long stick and kind of monitor those areas, look for concentrations. What we found is not particularly effective is ultrasonic. The amount of fluid flow required to get a reading on an ultrasonic detector is fairly high. It works well for things like air, but when it comes to ammonia, you're much more likely to smell it long before you'll be able to get a reading on an ultrasonic detector. Infrared thermography suffered from somewhat the same problem. In order to actually see that gas escaping in the thermal image, it took quite a bit of gas. You detect it by other means before the camera would. And then relief line detectors, they are excellent at detecting when relief valves open, but since they usually don't start picking up concentrations until around 3% of the lower flammability limit, which is well over 4,000 ppm, a leaking seat typically won't be picked up by that type of sensor. And so what we thought is a good way of kind of estimating a release rate per section 608 and just common sense is how much are you putting into the system. But a lot of systems will only put in ammonia every 3, 5, maybe even more years. So are we able to track the amount of inventory or charge of the system in between those fills? And so if you look at this picture here, there's kind of an area in the red box of fluctuating refrigerant inventory. Then that the evaporative condensers, they cycle on and off, they load and unload, they change a little bit, and then all that flows into the high pressure receiver. And the high pressure receiver that the cursor is going around now, that's where the ammonia is going to end up when it's not being used. And then when ammonia is needed out in the plant in the blue box, it's going to come from the high pressure receiver. So when things change in the blue box, it will pass through other vessels like that pumped recirculator with the 4 in it there, but it's going to eventually end up in the high pressure receiver. And that's because that pumped recirculator, it's a fixed, the level of that vessel is controlled. If the level gets high, there will be no incoming liquid to that vessel. It'll be stopped. And if the liquid level becomes low, more liquid is going to be put into that vessel. So if you track the average of that vessel, it's going to be constant. However, if you track the level of the high pressure receiver, it's going to go up and down as things change. So the question is, can we track the level of the high pressure receiver? And even though it's moving up and down as things change in the system, will it trend one way or the other? And will it trend downwards if we're losing ammonia? And so it turns out that the answer is typically yes, and you can actually make a tool to help track this. So this tool is you'll take the vessel where, and this could be more than one vessel, but in systems it's often just one vessel, and it's often the high pressure receiver. And all you have to do is put in the orientation of the vessel, horizontal or vertical, the dimensions, and the head type. 2:1 is the most common in this industry, but there are other options as well, just in case it's different. And then once that volume is calculated, you can move on in the tool. This is in Excel, by the way. You can move on to the next page, which is the vessel levels. And there it can input vessel level readings. You can input the date, the liquid level in inches, so that would be from the bottom of the vessel, and then either the saturation pressure or saturation temperature. You can pick which one you want to use. And so multiple instances can be used for any one date. You can put in multiple readings on a given date. You can skip dates as long as you go from line to line. Then once all the data is in there, you can push a button to plot it. And the plot that appears, it'll plot the raw data, which as you can see is kind of a scatter as things change, but it also plot a trend line of that data. And in this case, you can see that the trend line trends down at an average rate of 1,100 pounds per year. And you can also see the equation for the line, and the last number, the intercept, isn't important, but the slope of the line is the daily loss projection. And so what we found is if you plot over a large period of time, you can get a decent estimate. So in this case, this is the plant one we used. You can see the date range 2017 to 2018. And you can see a smooth trend downward. And that's because this plant, in their log sheets, for one log sheet, it would cover about a week. And so in this case, in order to input this data, we averaged the dates and the levels for each log sheet. And what you end up with this trend downward. And the average losses of this trend were 550 pounds, and their purchase rate is about 500 pounds per year. So you can see that this vessel actually tracks pretty closely with the actual purchase rate and the actual losses. So for this same plant, you can see now we're in the 2019 to 2020 range. And in this case, the vessel, it doesn't have a level probe, it only has sight glasses. So each time they do rounds, they log the number of sight glasses that have liquid. And the liquid is apparent because of the very dark sight glass. And so what you end up with is a lot of readings at the same level. But as they start to lose ammonia, they start to see more and more instances at a lower sight glass level. And so you can see that it still trends downward. It's essentially the same as averaging each page, except this is individually entered. And you can see that their loss rate has actually gone down from about 500 pounds a year to less than 400 pounds a year. And whether this could be due to a few reasons, it could just be that less maintenance was done in that time, but it could also be that emissions were reduced because in this time they actually removed a room's worth of evaporators and replaced it with a single unit to cool the whole space. And they were having mechanical integrity issues with those evaporators. So it's possible the maintenance and losses from those has gone down. And also they've been acquiring newer valves in the system as they and they were having some problems with emissions from those valves. So as they solve those problems, it could reduce emission levels as well. But we'll have to see if the trend continues. They aren't due to purchase ammonia for another year or two. So it's a positive sign, but it doesn't really prove anything, but it is a good sign. So a caveat of the dynamic charge tool is you kind of have to consider how the system operates as you go. So if you run into a situation where you start tracking this and then all of a sudden a large part of the system goes offline, you'll probably trend upwards because that offline portion of the system, all that ammonia is going to end up in the high pressure receiver. You're going to get an upward trending line. Or in the reverse case, if you start trending and then you turn on a large part of the system, you're going to get a much steeper drop, a much steeper slope downward than is the actual losses. So you have to keep those system fluctuations in mind as you do this. And then of course, if you expand the system or take things out of the system, you kind of have to start a new sheet because the operating charge of the system is going to change pretty dramatically. A small work probably won't have an effect, especially if the high pressure receiver is fairly large and full. But generally, if you're going to add or subtract equipment, you have to start tracking anew. And the tool is available for download via this link. And if you have any questions about it, you can always contact us, or bugs or things like that.
Okay, so that gives you a little bit of a sense of what we can use as sort of an independent means to identify, hey, do we have anything going on that it is a lagging indicator because we're sort of looking at trend over time, but it's a much shorter time lag than a plant would typically utilize, and that is, hey, we're running really low of ammonia level in our high pressure receiver. We need to add refrigerant to the system to top it off. And so we're encouraged by the initial findings of this tool as a shorter lagging indicator than what would typically be used in plants. So let's transition now and talk a little bit about what we found in the field. I had mentioned earlier there were 5 plants that were included as field work in this project. And among those 5 plants, we looked at 6 different refrigeration systems. Plant 5 had 2 systems. And what we're showing here is the operating charge of refrigerant in those systems that we determined based on detailed inventory or charge calculations. The purchase quantity trending over a period of time that we did the analysis. And so in plant 1, they were losing on average 500 pounds per year. So that translates to about 7% of their system charge. Thinking back to the initial survey question that I asked you, what's a, in your mind, a typical percentage loss? And so here's some sort of data that go along with that. Plant 2 is a slightly larger system, 15,726 pounds. They were losing at a higher rate, 2,369 pounds per year, or about 15%. Plant 3, the largest system that we looked at, 38,712. By the way, if you remember those larger than 10,000 pound systems that I showed you on that sort of bar chart, horizontal bar chart, if you averaged all of the RMP ammonia refrigeration processes, those systems that are primarily in food, NAICS codes, as well as refrigerated distribution, the average charge of those systems is 40,000 pounds. So this is sort of very near the average. This particular facility annually purchases about 1,838 pounds, or about 5%. Plant 4, 5,382 pound charge, 40%. That number's a little bit biased because they were doing some plant expansion, and there was some other things going on there, so that I don't know is reflective of their sort of normal situation, but it is what it is. Plant 5 had 2 systems, A and B. Plant A was 27,000 plus pounds, and they were purchasing about just under 1,600 pounds per year, or about 6%. And then Plant B, 15,000 pound system, and they were purchasing about 1,518 pounds, or about 10%. So Mark, what did we find?
So when we went out into the field, our first order of business was to prepare those charge calculations that Doug just went through. So that we measured all the piping, all the vessel levels, all the evaporators, and came up with those calculated charges. And then we went out to try and find leaks. And so we surveyed about 175 components, and we screened 159 and bagged 110. Some were just screened, some were just bagged, and some were both. So that's why the numbers don't exactly add up. But in the end, that's what we ended up doing. And we tried to get a wide variety of items, from valves of each type we could find, sight glasses, threaded connections, unions, different types of fittings, relief valves, pumps, and the purger. And we divided them into basically 2 pressure levels, high and low. High just meaning the pressure at which heat is rejected to the ambient, and low just pressures serving refrigeration loads. And we set the demarcation there at about 80 pounds. So a summary of the field findings, of those 175 items, only 34 had any detectable emissions. Most of those were sight glasses, a few were valves, and we had 1 compressor housing. If you've ever seen one of these compressors, it's usually made up of multiple parts that are bolted together. So this particular leak was found at a gasket where 2 of those parts are bolted together on the end of the compressor housing. We didn't find any refrigerant emissions from these other components. We know that these components do exhibit leaks, but during the survey, we just didn't find any from those. I mean, they do leak, but they weren't identified in the survey. And so when you kind of add up all those, the 175 points and the 34 leak sites, the average leak rate, this is in pounds per year. And so things that were triggered by an odor, so a smell was found and the leak site was pinpointed, those are only 1.25 pounds per year. And if you take all the components sampled, the average are 0.06 of a pound and 0.02 of a pound per year. And no low side components were found triggered by an odor. And so one thing you might notice about those numbers, as Doug will take over here and talk about, is just how small they are.
Yeah, that was a little bit surprising. And you might say, well, gee, how do you measure things that, I mean, 0.02 of a pound a year? Yeah, I mean, the techniques that were used as part of the field exercise and the laboratory work that preceded that, we can measure pretty low concentrations. And so, this was a bit surprising for us. And so hopefully you go, wow, okay, well, the good news is, Mark, remember he said 34 of 175. So we didn't go out and find, ammonia blowing out all over the place, which was good. But remember, I said our null hypothesis was that the quantities of ammonia that these plants are purchasing is due to fugitive emissions. They just don't know. There are valves weeping outside up on the roof, and collectively they add up. Yeah, they do, but they don't add up to thousands of pounds a year. So what's going on? Where is this refrigerant being lost? And so we kind of had to back into it, and this is what our sort of follow-on belief is now. So if you think about the refrigerant that's lost from these systems, we kind of put it into 2 major categories and then 2 minor categories. Known losses, but known intentional and unintentional. So an example of a known loss would be venting. So it's pretty routine for these systems as part of their maintenance activities when they're pumping down a part of the system to be able to open it up and do inspection, service, maintenance, repair, replacement. They need to remove the ammonia, and they commonly do that by venting. They would vent the vapor to atmosphere. If there's liquid or residual vapor, or if they're in a location where they can't vent to atmosphere, they would typically vent that ammonia to a water tote, and the water readily absorbs the ammonia, and then they would treat that ammonia, aqua ammonia solution. In the known category, but unintentional, these are accidental releases. Typically, the accidental releases are attributed to the loss of mechanical integrity. Pinhole leak, crack in a pipe, crack in a connection, gasket failure. I mean, something where they've lost the pressure boundary of that system and now they have an uncontrolled leak. They know about it, but it was unintentional. The other thing that we've seen with some increasing frequency is pressure relief valves activating, and in some cases, these are valves that activate at below their set pressure, so we would call that a valve failure, but we'll call it failing safe. These relief valves, when they do actuate, they can move a fair quantity of ammonia. If you look at their stamped flow rates, they're fairly high. They don't stay open continuously, but when they do actuate, they can discharge a lot of ammonia out of the system very quickly. In the unknown, there are accidental leaks that fall into this category, and these can stay sort of latent or hidden from our view for some period of time. And I would say the two biggest pieces of equipment that fall into that category are leaking tubes in evaporative condensers. The water that we use in these evaporative condensers readily absorbs the ammonia, and that can sort of mask the leak for days or weeks. And then malfunctioning purgers, auto purgers, these are removing non-condensable gases from the systems. When they do malfunction, again, there's a water bubbler that the residual non-condensable gas is expelled through. And if we discharge ammonia through the purger, we may not find it readily. And then lastly, the lowly fugitive emissions that Mark showed you how low the rates are. So if we're going to reduce the losses from these systems, it's really keying in on what we know, and also paying attention to these accidental leaks that we don't know. The fugitive emissions, we can tighten things up, but that's not really where the action is. So to kind of put this into a little bit of a context, this is a bit of a cartoon, but we thought we'd structure this in terms of severity or the quantity of ammonia that's lost, and then the frequency at which that occurs. So this has elements of kind of like a risk matrix, what we would typically use in a risk matrix. So the large scale accidental releases, we can lose a lot of ammonia in those events. Fortunately, they don't happen with great frequency, but when they do, they're significant. These sort of modest leaks where we have an accidental release, a cracked fitting, a broken nipple on a piping segment, they happen with somewhat greater frequency, but they're fairly quickly controlled at the plant level, and so they still result in a loss, and we would want to prevent that. The maintenance leaks, this is the venting and the purging. A lot of systems, depending on the activity that they have in maintenance and repairs, equipment replacements, expansions, this will vary based on facility, but for most facilities that are undergoing some change, especially process plants, there's a lot of work going on in those systems, and so there's venting and losses associated with that. And then this fugitive emissions is way down here in sort of the weeds. Small rates, high frequency, they total up into the tens of pounds per year, maybe for a plant. A large plant might be 100 or so pounds a year. And then, we've done a good job, I think, in the industry at controlling this last one, and that's theft. We had a pretty big rash of this 10 or 15 years ago. I think it's sporadic now, and that is the stealing of ammonia from these systems. And you're kind of thinking like, stealing ammonia? What the heck are we stealing ammonia for? Well, there's some people that value the ammonia for clandestine operations like running meth labs. So in some cases, where portions of a system are accessible. These are largely in rural areas. People can come on site, find a connection, hook up, and away they go. So one of the big emphasis, I think, take home from our perspective is reducing these accidental releases that are rooted in the loss of mechanical integrity. And I think that's going to be a big lever to reduce the consumption, to reduce the releases of ammonia. And that is making sure that we're doing inspections, tests, maintenance, and retiring equipment before it fails. And so plants that are covered above this 10,000 pound threshold that are covered by OSHA's process safety management, EPA's risk management plan programs are compulsory required to have mechanical integrity programs. So I think we're getting better at that, and we have some tools and resources that are enabling plants to make continuous improvements there. So when they have strong mechanical integrity programs, the probability of those accidental releases goes down. That's good news for the plant. They're able to run more effectively with less disruption. I would point out that both from a regulatory perspective, both OSHA's National Emphasis Program and EPA's National Enforcement Initiative that have done a number of inspections in ammonia refrigerated facilities, I would say the number one cited element in terms of deficiencies is mechanical integrity. And we have good data on that over a longer period of time from OSHA. And I think as EPA's National Enforcement Initiative sort of rolls forward, that will just reinforce that. So we included on this page a link for additional resources that you can go for related to ammonia, and there's some others that we'll talk about at the end. So in sort of wrapping up here, we want to save some time for some question and answers as well. So if you haven't had a chance, just chat in your question and we'll get to those. But sort of wrapping up here, the good news is that this sort of odor reporting that Mark referred to, this is internal, where someone in a facility smells ammonia, they let their utility staff know, and the utility staff responds promptly, and they find where the emission is occurring, and they take action to get it repaired, get it stopped. And so I think plants have done a really good job with that, and so that's a good thing. Mechanical integrity, I think that's still a challenge for a lot of facilities, especially older facilities or facilities that were built over a number of different eras. We're still sort of learning, we're still sort of growing, and I think we're seeing some positive moves in that direction, but it's going to take time. There's some plants, and we kind of checked in with others. We visited 5 plants for this particular project, but we have a network of a lot of other facilities that we engage with, and very few of them will search for fugitive emissions as sort of an ongoing, normal, we'll call it a PM, preventive maintenance activity. Some plants do set a threshold that says, hey, if we're purchasing and we're using more than 5% of our system's charge on an annualized basis, then we're going to go out and figure out what's going on. Why are we losing ammonia? So if they see an uptick, they'll go after it. Keep in mind, though, oftentimes this is a much more lagging indicator than what we're proposing, and I think what plants will find if they implement the dynamic charge calculation that Mark talked about. We still sort of suffer a little bit from the economics here. Ammonia is cheap. It's about $1 a pound. So some of the fluorochemical refrigerants, the newer HFCs and HFOs, are significantly higher cost. Those refrigerants just aren't used in these systems. So, there's a bit of a challenge where, the refrigerant cost is cheap, and that's one of the reasons why it's vented. So, and lastly, some plants don't really have this loss benchmark. Like, what is a reasonable amount that we should be able to target for our system in order to keep the emissions down below some reasonable level? So this is a bit of an eye chart. I'm not going to go through this in all sorts of detail, but let's focus here at what our recommendation is. So plants really should kind of set a threshold of 5% per year of their system charge, and not to exceed 2,000 pounds a year. So, a ton of ammonia a year. Now, you think about that and say, well, gee, that seems sort of like a lot. Well, it depends on how big the system is. If you look at a average size covered process, a 40,000 pound system, 5% losses is exactly 2,000 pounds a year. That's 5.5 pounds per day on average. And so if you looked at on the larger end of that spectrum, a 400,000 pound system, if we said limited to 5%, all of a sudden you're at 20,000 pounds a year. Wow, that's a lot. That's 55 pounds a day. So that's not really reasonable. So that's sort of, you have to look at the scale of this infrastructure and, sort of block things a little bit and not just say, go on a percentage and, hey, 20,000 pounds a year, that's what we need. I think we can do better than that. So some of this is really setting an initial percentage of the system charge and then setting sort of an upper limit as a, hey, let's see if we can target and maintain that. And so they're not too different than what we saw in the field and what we've sort of just kind of checked in with other end users where they're at and the quantities that they're consuming as a percentage of their system charge. So I want to just wrap up by extending a few thanks to both EPA Region 5, Christine Anderson, who's the P2 coordinator, and she's been our primary contact, and Antoinette Hall, who's a project officer. They were both very helpful on this project. I appreciated their input, their guidance over the last 2 years. So thanks to both of you, Christine and Antoinette. Here's a summary of the tools that are available to you as a conclusion of this project. Mark didn't talk about the bagging tool, but that is a tool that you can actually calculate the fugitive emissions if you apply this bagging technique that's covered in more detail in terms of how-tos that are in the guidance document. And then I also want to just make sure that you're aware there are some resources related to ammonia refrigeration to point you to. The International Institute of Ammonia Refrigeration, a great resource. They publish a suite of standards that apply to this technology. They have an annual conference, education programs, so really a great resource for the industry. Here at the UW, we have the Industrial Refrigeration Consortium. We maintain a website, staff, and we're engaged primarily with end users. And then for technicians to kind of get them the education and training, it's just another sort of network of resources available for helping staff and facilities further their knowledge, skill, and capabilities. So with that, I will stop here and let's see what we have for questions.
So as the first question, was ammonia loss during oil pot draining determined? As part of this project, we looked at oil pots a little bit. We don't think it's large. The amount of ammonia actually dissolved in the oil is quite low, but we weren't able to actually get measurements of that. Now, if you're bringing out actually flowing vapor ammonia or liquid ammonia as part of your oil draining, that's a little different. But if all of the liquid ammonia is boiled off and the oil pot is isolated, it's likely just fractions of a pound. It makes a huge odor when you drain oil, but it takes so little ammonia to make that big odor. It's probably very small, but no, we weren't able to measure it. So next question. In regards to quantifying accidental ammonia releases, do we offer tools for release calculations? There are 2 papers published by Doug and Todd through IIAR. And if you want to look at the guidance document, those papers are referenced there. And those go through in pretty good detail on how to calculate the quantities of ammonia released during an incident. Another question, I didn't see compressor shaft seals in components surveyed, and in their experience, plants with high fugitive emissions were ones with reciprocating compressors and shaft seal leaks. Shaft seals, I tried to bag a couple of shaft seals, but it just proved too difficult with the amount of air moving off in the motor. But on the plus side, any odor coming from the shaft seal would indicate a leak. It takes a lot of ammonia, or it takes a very small amount of ammonia to make a big odor. And if you take a look at the guidance document, we have some correlations between screening values and release rate. And so if you're able to screen that shaft seal, you can actually get an estimate of the release rate that way and kind of just gauge how large it is. But in terms of actually bagging shaft seals, we weren't able to do that. Has there been any calculation of energy savings that result from leak repairs in these systems? The odds of the lost ammonia impacting the energy use of the refrigeration system is pretty low because these systems operate with excess liquid in reserve. So in your household air conditioner, yes, it would use more energy if you lost refrigerant, but that's a critically charged system. These industrial systems are not typically, or they're essentially never critically charged. So if the system reached a point where energy use was impacted, they would be seeing other issues as well, lost temperatures, lost product, and so it's not likely to get quite that bad. Fugitive emission. Oh, go ahead.
Oh, sorry, I wanted to comment back on the oil pod draining to just point out that, or clarify, I'm thinking that the question relates to the emissions or off-gassing ammonia that might be sort of dissolved in the oil, as opposed to I'll call it operator error in letting ammonia come out after all of the oil has been drained from the pot. So I'm assuming it's the former. And this is one sort of experiment that you all can do if you have a facility. That when you drain the oil comes out, it's fairly frothy. It kind of has a consistency like a milkshake, a chocolate shake. So fill your pail bucket up to a defined level, mark that level on the pail, and then let the ammonia off gas, and you'll see that the apparent level will decrease over time. And then come back, mark the change level, and determine what that volume is. That's going to be ammonia that's off gas. And if you actually took the density of ammonia at atmospheric pressure and whatever the normal temperature is in your location and calculated it by that volume decrease, apparent volume decrease, you're going to find it's a really, really small number. So the off-gassing due to oil draining, that's like another example of fugitive emissions, and is down in that, hundreds of or thousands of pounds per year sort of category. Sorry, Mark, go ahead.
No, okay. We'll just move on to the next question. In regards to purgers, did you estimate losses from properly operating purgers? We did. They're very small. It's on the order of tenths of a pound per normal purge, even hundredths of a pound depending on the suction level. That is a properly functioning purger. Even 100 purges a month might add up to a couple of pounds a year. The thing is, if a purger is not operating properly, you can easily lose 1.5 pounds hour. So it really just, a properly functioning purger, very small. A improperly functioning purger can lose quite a bit. So monitoring the purger is fairly important. And more details on that in the guidance document as well. So during field work, did you find further info on preventing large accidental releases? Really, this falls back onto mechanical integrity and proper design of systems. Are your relief valves properly sized? Are the set points appropriate? And are you maintaining your mechanical integrity? We didn't really look at that as part of this project, but just industry experience has showed us that. And the last one, any difference in leaks found, the leak rate between inside and outside? We did find many more leaks outside than inside, especially with valves. However, 80% of the valves in the industry are outside. So in terms of percentages, you're likely to find more leaking valves outside just because there are more valves outside. And we found so few leaking components in general that weren't picked up on an odor report that it's hard to draw any conclusions there. If you talk to plant staff, they might indicate, well, these leak a lot more, and there might be suggestions of temperature fluctuations, things like that. So it likely plays a role, but at the same time, it's hard to draw a conclusion from the work done here.
And just one other follow-on the mechanical integrity. So last year, IIR did publish the first version of its a normative language maintenance standard. It's IR standard 6, and so I would refer you to that as sort of a tool to be able to incorporate into improving your mechanical integrity programs in the facilities. That sort of it replaces some guidance related documents that they had for some period of time, IR Bulletin 109 and 110. And then in 2016, we published a fairly extensive mechanical integrity guidebook, and that's another sort of potential resource that would supplement IR Standard 6.
So there's just one last question about relief valves sweeping within maybe 10% of set pressure. Yeah, that can get, those can add up to pretty substantial amounts. Most plants don't operate routinely within 10% of the set pressure. But if that was the case, yeah, you could lose substantial amounts. In our experience, the weeping doesn't typically start until within about 1% of the set pressure. But as valves age, that can drift downwards. So
we've also had we've done a lot of postmortem testing of relief valves, and most of those we've received as a consequence of the plant experiencing that valve opening at a pressure well below set pressure. So a 250-pound set pressure valve, the plant says, hey, it opened at, we never saw the pressure go above, 140 PSI. So, we've been postmortem testing those valves on some frequent basis, and those are, I guess, what I would refer to as failing safe. So. Okay, so look for a email. I'll send out a PDF of this presentation. Thanks everybody for being online. Stay safe, and let's get after reducing losses from our ammonia refrigeration systems.
Great. Thank you, Doug and Mark, for your presentation, and a big thank you to everyone who was able to join us today. We hope you found this webinar helpful. So thanks again, and I hope you all enjoy the rest of your day.